Hi, so I'm Yee-Jian. I'm going to talk about something maybe you can relate. So after a whole week at types, you're like, oh, this is so long. When does this end? When does this terminate? And and well, good news. This is the second to last presentation. So let's do this. So Rocq is based on the calculus of inductive constructions, which means it has inductive types. And to construct terms of inductive types, you use constructors, but the type theory designer can choose to either eliminate inductive terms with either eliminators or using fixed points and match. Fixed points here just old camel-led regs if you don't know about fixed points in Rocq. So for example, this is okay, I did a mistake as everyone did. Yes, so that's the add fixed point, and the advantage is the extractor code is idiomatic, means you have a native recursion. But if unrestricted fixed points can be non-terminating, for example, this boom, in this boom, when you apply anything of type net to it and gives you a term of false and breaks consistency. So we don't want that, and that's what the dot checker does. It checks for structural recursion. So what you can do is you can have a recursive argument, and you can show that. So the gut checker checks that all the recursive calls in the body are getting smaller on the recursive argument. That's it. Simple. Let's see another example. For example, this is minus. It's typical. 0 minus something is 0. A minus 0 is A, and then there's a recursive case. Easy. That is accepted. And you have diff, which essentially minus n suitably many times from m, or the recursive k. And then surprisingly, diff is not guarded. Why? Yeah, someone marked the answer, and the answer is 0. Because when 0 is substituted into the minus over there, it is not a subterm of m, and therefore it does not terminate. And you're like, okay, maybe the gut checker is not that easy, and I'm going to show you the gut checker of Rocq, and it looks like this. So it's about 1,000 lines where the sub-procedures, no one kind of knows how it works. Iterated by many different authors over 30 years. We have one in the room at the back. And it has multiple dimensions of complexity, which you will see later. So this was my internship project with Yannick Forster last year, and there are two contributions. One is I have an implementation of Rocq's gut checker in Rocq using the Meta Rocq project, which is extending previous work by Lena Gea. And there is documentation, which is my internship report. You can get an example of how it works, and I give explanations as well, which I will show you. It's available on Hull. Okay, if you don't know about the Meta Rocq project, you have heard about Lean in Lean. Meta Rocq project, in short, it formalizes Rocq's type theory in Rocq, a faithful one, and then there is a verified type checker, verified extraction. But the important thing here, it is parameterized by a gut checker. So when they implemented, they didn't know how it works, so it is parameterized. Okay, so the implementation, my implementation looks like this. You can import the plugin, which I wrote. Define fixed points as you would. You can code the syntax into a AST term object here, and then you can run my favorite little function there, which takes a term and gives you a bool, guarded or not guarded. And here it says yes, so you're happy because your addition is actually guarded. Which means terminating. Yeah, okay. So I'm going to go very quickly over the history. You can look if you are interested. So basically, the first gut checker was well, it was Coq. I did a Control G, and then it didn't work well. And it was written by Christine Poulamorin, and in 1996. And then she and her PhD student Eduardo Jimenez wrote some specifications. In the 90s, okay, all is good. Until 2010, Pierre Boutier was implementing the vectors library. And if this might look familiar to you, if you heard the word the convoy patterns, so he was writing the vector library, and he thought that adding this thing which is called beta iota commutative cut subsum rule. It will help the implementation a lot, but there is a Christmas gift that came with it in 2013. So 2 weeks before Christmas, Daniel Shapler wrote to the Coq Club with an email that has nothing but a piece of Coq code that ends with a proof of false, and signed off by like yours truly, Daniel Shapler. So of course we need to put off the fire. So 2014, Maxime Dennis restored compatibility with propositional extensionality, which means that Rocq is compatible with hot as it should be, and with other extensionality principles. Okay, PMI is saying maybe. Okay. Hugo Ebelin also implemented some new features recently, strong normalization and extruding uniform parameters. Okay, let's have a taste of the gut checker. This might help you because you've seen too many unguarded fixed points when you try to do it. We're going to use our favorite example with addition, and we want to check that it is guarded. What does it mean that this is guarded? Guarded means that all recursive calls have a strict subterm as the recursive argument. So every fixed point has a recursive argument. Written by struct M means that the 0th argument is a recursive argument, and then it is the recursive parameter. So every term has a subterm specification, which means that, for example, M is a large subterm with respect to M. M prime obtained from destructing M is a strict subterm, okay? And N, for example, is unrelated, so it's not a subterm. Second concept you need to know, there are 3. So this is the second. There's a gut environment. You just store everything that you have seen and record its subterm specification. For example, you can see that N is unrelated, M is large, and so on. There is a stack of subterm specifications, which when you're checking an application term, all the arguments of your application, function application, has their subterm specification stored on a stack. So that's it. For example, here you have M and Sn. Okay, let's go. So initially, you have the add, you define it like this. Every parameter after the recursive parameter are cut and turned into lambdas. So for example, N, here you have a big lambda. And then to check the guardedness of a lambda, you need to check 2 things, the binder type and then the body, because we are independent types, so the types can depend on terms. So clearly this is guarded, hopefully. And the body is up. So now we check the body, right? The body is checked with an updated guard environment with N now, because we enter the body of a lambda. And the body is a match. For a match to be guarded, 3 things to check: discriminant, return type, and every bunch must be guarded. So let's go. Determinant and discriminant and the return type are guarded. There are no recursion calls, so this is fine. To check a branch, you expand into lambdas, specify the parameters of the lambda, and check the lambda. For example, the 0th branch has no parameters, so there's nothing to specify, nothing to specify. And then the lambda itself is N, which has no recursive call, therefore it's guarded. First branch, expand into a lambda, you specify the parameters, and now the magic starts to happen, because the parameter is M prime, and the M prime is obtained from destructing M, which is a large subterm, therefore M prime is a strict subterm. And then, so it is put into the stack, and now you can check the whole lambda. You remember, if you check lambda, you need to check the type, but the type is net, so whatever. It's fine. And then you push the stack into the environment before you enter into the lambda. Now you enter into the lambda. And then in the body of the lambda is an application. So now this is a key case, because there are 2 things to check. One is all the arguments, which are all guarded by themselves. And then the call itself is a recursive call. Therefore, the recursive argument, remember, it is the 0th parameter, needs to be a strict subterm. So we just go through it. The arguments have no recursive call and therefore are guarded. And then the stack is populated when we are checking the arguments. Now we can check the head of the application. The application, now you look at it, since the recursive parameter is at 0, you look at the 0th element on the stack, which is a strict subterm of the recursive call of add, and you're happy because you have a strict subterm on the recursive call, and therefore it's guarded. Okay, all is good. So there are more features that are not in this example. So for example, what if you delay the application of M, you delay giving M to this, the stack handles this well. What if you try to fool the guard checker a little more, you put identity here, you have a pred suck. Actually, it works because there is some weak head reduction going on when you're trying to specify a term, right? So when you weak head reduce these terms, they are fine. But you do not do weak head reductions everywhere because that will lead to weak normalization. For example, here, if you weak head normalize the body, this empty let will be gone. But this empty let has a clearly non-terminating subterm. So there is this thing called a redax stack, which stores all the redax and reduce when needed. So it is a complicated beast. And you have seen, so now there are at least 4 dimensions of complexity because they stack on top of each other. So we have seen a stack. We have heard about the strong normalization with a redax stack. And then there's support for mutual and nested fixed points, which creates a auxiliary regular tree structure to record how the inductive looks like because it could be nested or mutual. And then OCaml, the implementation has lazy peppered everywhere. That's why it is so big as it is now. And what I've done in this project is I have a full implementation, and then it has a test parity with the kernel whenever my implementation holds, because there are some opaqueness issues. So, the code is freely available. Conclusion. So I have a code. I've coded the guard checker of Rocq in meta Rocq, and we have a documentation / report on HAL. And the future work, interestingly, the guard checker itself is, I have to disable the guard checker when writing it in Rocq. Because it does beta reduction, which is not clear to be smaller in any way. Future works will be write an abstract guard condition and verify that the guard checker actually follows this condition. Now you can try to go to talk about how sound this is. So that is all for my presentation. Thank you.